Hey guys, this is 7.4 and we're going to be calculating the equilibrium constant. In this video, we will quantitatively define the relationship between the reactants and products once equilibrium has been reached. I am Trevor Stock, an AP chemistry student and a senior at Bayport High School in Green Bay, Wisconsin. And let's get started. So you might be asking yourself, what is the equilibrium constant? Well, the equilibrium constant of a reaction K is the ratio between reactants and products based on concentration once the reaction has reached equilibrium. Q is used to determine when equilibrium will be reached. Shown here at the bottom, when the reaction is still kind of deciding when it's going to reach equilibrium, Q helps to kind of determine the changes that we see. And then Kc or Kp for concentration or pressure is used to determine the ratio once equilibrium actually has been reached. So Kc, excuse me, is found by dividing the concentrations of products by that of the reactants, and Kp can be derived by dividing the pressures of the products by the reactants. If K is greater than 1, then equilibrium favors the products. If K is less than 1, then equilibrium favors the reactants, meaning that the equilibrium, the amounts of reactants and products will be different amounts for each. It's not always 50-50. So it'll usually favor one or the other. And pure liquids and solids are excluded from most equilibrium expressions. We usually just use gases. So how do we calculate the equilibrium constant Kc? Well, first we got to identify the chemical equation. If it's given to us, that's great. Otherwise, we got to find it. And we got to write the equilibrium expression for Kc, which is the ratio of the products divided by the reactants. And then lastly, we got to plug the values of concentrations into the expression and solve for Kc, which is our equilibrium constant. And I just have a simple example down here at the bottom. So we have A2B breaking apart, creating C and D. At equilibrium, the concentrations of each gas are found to be 0.1 molar for A2B, 0.4 for C3, and 0.6 for D. And we just got to calculate the equilibrium constant Kc. So first we get our chemical equation. So 3 A2B changes into 2C3 and 2D. And then we get our equilibrium expression for Kc. So that is just our ratio of products divided by the reactants. So we have C3 and the coefficient turns into an exponent there. And then same thing for D here, since we have 2D here. And then A2B, we have a 3 as a coefficient there, so that turns into exponent or power to 3 as well. And then we plug in our values of the concentrations for each one, and we end up getting 57.6 after doing a little bit of simple algebra there. So that means that this one is in favor of the products, which are on the numerator side of this fraction. So I have multiple choice practice here for the concentration constant. And this is 3x plus y turns into 4z. And you can also have the reverse reaction. So the reaction mixture represented above is at equilibrium at room temperature, 298 Kelvin. And the molar concentrations are x equals 3.0 molar, y equals 1.5 molar, and z equals 2.0 molar. What is the value of the equilibrium constant for the reaction at room temperature? So we have a variety of possible answers here. And for our solution, we're just going to have products over reactants, plug in our values, and we end up getting 0.395, which is C in this one. And since that is less than 1, this equilibrium favors the reactants, meaning that when we reach equilibrium, there'll be more reactants left over than products that are switching back and forth. All right, so how do we calculate the equilibrium constant of pressure, which is Kp? So just like Kc, the equilibrium constant for concentration, Kp is the equilibrium concentration for pressure, and we have a few different units for that. And if you ever need to convert between the two for Kc to Kp, I have just a couple of converting formulas just for reference here. I don't know if we really hit on them too much in 7.4, but if we ever need them down the line, we have them here. And I just have a quick example for calculating Kp. So we have reactants A and B combining together to form product C at standard pressure. if equilibrium is reached at double that, what is the equilibrium constant for Kp? So I just have a basic chemical equation here, and we have the pressure of C to the power of 2 because of the coefficient here. Then we divide that by the pressure of A to the power of 1 for the coefficient, and times the pressure of B to the power of 2 for the coefficient there. Then we sub in our values. We only consider the pressures when they have reached equilibrium. So the 1.0 ATM pressure does not matter here. We only consider the 2.0 since that is the equilibrium one. So we sub that one in for each of our reactants and products here, and we end up getting 4/8 or 1/2 in this one, meaning that the products, reactants were actually favored in this one since P is less than 1. So here's just another multiple choice practice here. So we have 2H2O changes into 2H2 plus O2. So H2O decomposes according to the equation above when pure H2O is poured into a flask at room temperature, which is 298 Kelvin in this case. The pressure in the flask is originally at 1.0 ATM, standard pressure. After the reaction reaches equilibrium, the total pressure in the flask is 1.6 ATM. What is the value of Kp for the reaction then? Still at room temperature as well. So Kp is 1.6 power 2. So that's just for our hydrogen gas here. And then times 1.6 power 1 for our oxygen gas based on the coefficients that they have. Divided by 1.6 to the power of 2, coefficient of H2O here. And we get 1.6 over 1 since these two here will cancel out. And we just get 1.6, which is B here. And based on 1.6, this reaction is slightly in favor of the products, but just by a little bit. So there'll be a few more of the H2s and O2s running around than the H2Os at the end. But they'll still be switching back and forth in equilibrium with the forward and reverse reactions. So what can we take away from all this? Well, Kc and Kp are each equilibrium constants, both of which are ratios calculated from given concentrations or pressures in the problem. The rate of reactions and the balance of the equilibriums are altered with changes in concentration, pressure, temperature, etc. Based on our calculated K value, we can better understand the state of a reaction equilibrium, even without a graph, which is pretty nice. Sometimes with a graph, we can just kind of judge based on there what has more or less at the end. But if we don't know, we can always have the peace of mind that we can calculate that. And we also know that reactions could change slightly even in equilibrium. They'll change back and forth, but remain pretty constant. And solving for K is a nice approximation for the ratios that they'll end up with in the end. I just have a funny cartoon here. And thank you guys for watching. That is all for this one. I just have a few sources at the end for the pictures and research and whatnot. All right, thank you.